Over to you, Aditya.
Yes, sir. Thank you for the nice introduction, sir. So, hello everyone. This is Aditya Shankar, and as sir has introduced, so I'm in the last year of my PhD. Okay. So before we dive into today's class, so I would like to know how many of you have known or have worked in deep learning, or if you know a little bit, that's also fine. So we will start from scratch. So you can just raise your hands if you have studied deep learning at some point.
I see only a couple of hands,
Okay.
so you have to assume that most of the
Hmm.
students, I mean, that is not expected also, so it's okay. But this,
Okay.
since this is section two, I think they have good Python knowledge. That's what was the expectation. So, okay, six hands so far. So
Hmm.
that's fine. Thank you.
Yeah. Okay. So I hope
Carry on.
my yeah. So I hope my screen is visible to everyone, and please feel free to interrupt me whenever you have a doubt. Okay. Okay. So yeah. So we will start with the difference between the traditional machine learning and the deep learning. Okay. So if you look from the feature extraction perspective, so in traditional machine learning, like I think you have gone over the algorithms like decision trees, SVMs in previous classes. So you must have observed that mostly the feature extraction part is domain specific. For example, like if you have images, then you need to extract some features from it, or you have to do some processing to the image. Okay. So that is what you need to do for traditional machine learning algorithms. But what happens in deep learning? So deep learning is you just pass the image to the network and it just automatically extract the features and you are able to accomplish your desired task. Okay, so examples of traditional ML. So as you already know, the decision trees, SVMs, KNNs, these are all the traditional machine learning algorithms. And talking about neural network and especially deep learning networks. So these are the CNNs, the convolution neural networks, the RNNs, and the transformers. So in today's class, we will be studying about multi-layer perceptron, MLPs, and CNNs. And for tomorrow's class that is scheduled, we will understand transformers in depth. Okay. Okay. So talking about the data requirements about the traditional machine learning algorithms, Nafis, I think, do you have some doubt?
Yeah, if you could recall your hands up, because I think that was for the earlier question.
Okay.
So you you can retract your, yeah, please go
Okay.
ahead, Aditya. Yeah.
So talking about the data requirements, so you all know that the traditional ML algorithms work well with like small to medium data sets. So like for example, if you have 100 images or 200 images in your training set, so you can expect the traditional machine learning algorithms to work well, which you cannot expect in case of deep learning algorithms because they are too data hungry and they usually require a large amount of data. Okay, so like talking about the interpretability, so the traditional machine learning algorithms are more interpretable than the black box deep learning because in deep learning you just supply a image or you can supply a text to a model and anyone doesn't know what's going on inside it. Okay, so the traditional ML algorithms usually take lower time to train and deep learning, like as you know, like they are data hungry and they require very large hardwares for training, so very powerful GPUs. Okay, you must have heard about the NVIDIA GPUs that are used for training the deep learning models. Okay, so we will start with linear regression first. So you must have idea about the linear regression, right, everyone? Okay, okay. So in linear regression, so you try to calculate one variable using the other variable. Okay, so basically y equals to wx plus b, where w is the weights and b is the bias that we need to learn. But what happens if the relation is not linear, right? So, for example, if you have some gene expressions, and if you want to predict some like MIC values, or giving you a simple example, like suppose you have some images, right? And you have their labels. So cats and dogs images, and you have their labels, right? So the relation is not linear, right? So we need to add some non-linearity to it. Okay. So the main limitation of the linear regression is it cannot model the complex non-linear relationships. Okay. So we have the problem. So we have to look for some solution. So the solution is like take the linear regression model. Okay. And we are going to add a non-linear function. Okay, we will talk about this later. These are basically called the activation functions. And we are going to stack a lot of them, right? So stacking a lot of them means, say, suppose this is linear, this is a linear regression model, so wx plus b. So you apply the activation function to it, and then you use it as an input to another regression, right? So w2 h1 plus p2. Okay. So you can interpret this as the first, this layer, this learns the feature transformation, and the second layer, uh, maybe you can say that it performs the regression in the transform space, right? Okay, moving forward. Okay, so if you have understood somewhat until here, then you have understood the basics of the multi-layer perceptron. So now we will like know some details about the technical concepts of the layers of multi-layer perceptron. Okay, so this is what a typical multi-layer perceptron looks like. Okay, so basically we have an input layer from where we give our data as input, and we have the output layer. Okay, and all the layers in between, these are the hidden layers. So this is basically inspired from how the brain works, the human brain works. Okay, so this is how MLP is. Okay, so now we were talking about the activation functions. So like these are the functions that we were applying to the result of a regression, which was used to add non-linearity into the model. So as you can see that these are the input. Okay, one, two, three, four, five. And for, say, suppose this layer, I think you can follow my cursor. Yeah. So first we will do a weighted sum of all the values. Okay. And then we will just apply the activation function, right? So there are several example of activation functions. So you can see that you have the sigmoid, the tanh, the ReLU, leaky ReLU. Okay. So for different purpose, like different activation functions are used. But the most common function that is used for the images is the ReLU, right? Okay. So with if you don't add this activation function, and if you like just pass the data, okay, then it goes to the next layer, then again the result and goes to the next layer and so on. So it will just be like a simple linear regression. But activation functions add non-linearity into the deep learning. Okay, so let's see some basic examples of multi-layer perceptrons, right? Okay, does someone have any question until here? So I can clear it, or else we can just move on.
Sir, I had a question.
Yeah.
Which activation function is best suited for what purpose? Like we know so many examples of them, but why so many? Which one is applicable where?
So basically, like the activation functions are chosen based on a like trial and error basis. Okay. So for example, uh, yeah, you must have a mathematical intuition behind it. For example, so why do you need the ReLU? So ReLU is basically max of 0 or x. Okay. So in images, it is mostly believed that like the negative values don't have any meaning. Okay. So like uh, if you know the images, so you must know that the pixel intensity values are between 0 to 255, so which are normalized to 0 to 1. Okay, so what does that negative means? Right. So you don't have any meaning for it. So that's why for most of the images, the ReLU is used. Okay. And like this is on a trial and error basis. So maybe you can apply the other activation functions too. And if you can improve upon the results. So that's the main purpose. And you have seen some other functions like is it yeah some other functions like leaky ReLU. So this was just the modification of the ReLU. Okay. Yeah, so like the functions, they also have their advantages and their limitations. So for example, uh, the sigmoid function suffers from something as vanishing gradient problem. So we will look into that. Right. Does this answer your question?
Yes, sir. Thank you.
Okay. Okay. So moving on to the basic examples. Yeah. So is my board visible to everyone? Okay. Okay. So, I think you all must know about the two input OR gate, right? So let us draw the truth table for it. Okay. So 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So the output is 0, 1, 1, 1, right? Okay. So let us plot this first, right? Okay. So suppose this is our x1 axis and this is our x2 axis, right? Okay, let's choose some other colors. Yeah. Okay, so this is 0, 0, and yeah, so this is 0, 1, 1, 0, and this is 1, 1, right? So can you see that this is linearly separable? I mean, you can just draw a line. Okay, so above it, if every value is 1, and below this, the values are 0, right? Okay, so let's suppose we are given the weights, right? For now, let's suppose that we are given the weights. Okay, so just okay, so let's draw a basic multi-layer perceptron. Change. Suppose this is x1, this is x2, and this is y. Okay, and let's add a bias to this node, output node. Okay, let's say the bias is 0 minus 0.5, right? Okay, so let's test for all the 4 cases, right? So let's say what happens when we take the case 1. So for case 1, our x1 is 0 and x2 is 0. Okay, so one important thing is we need to consider the activation function, right? So for the activation function, let us take the step function as the activation function. So it is 1 whenever x is greater than or equals to 0, and 0, right? Otherwise. Okay. Okay. So let's see the case. So when x1 is 0 and x2 is 0, and let's say someone has provided us the weights as 1 and 1, right? Okay. So what will be the value at y? So y equals 0 into 1 plus 0 into 1 minus 0.5, right? Clear until here? Okay. And when you apply the activation function to it, okay, so what will this be? So this will be 0, right? Okay, so our first case is matched. Let's move on to the case 2. So case 2 is x1 is 0 and x1 is 1, right? So what will be our y? 0 into 1 plus 1 into 1 minus 0.5, right? So what is the value? 0.5. Okay, and when you apply the activation, so it becomes 1, right? So you can see from this case will apply, right? Okay. So for the case 3, so x1 is 1 and x2 is 0. So for this case, y is 1 into 0 plus 0 into 1 minus 0.5. So this is again 0.5. And when you apply the activation function, it again becomes 1. And for the last case, so when you have x1 is 1 and x2 is 1, so you have y equals to 1 into 1 plus 1 into 1 minus 0.5, right? So you have 1.5 and this again goes to 1. Okay, so you can see how this MLP solves the two input or gate problem, right? Are you convinced, or like if you have any doubts, so you can just unmute yourself and speak? Okay, I think no one has any doubt, so let's
Sir,
move on. Yeah,
sir, what are the activation functions and like are there like the limit functions?
I mean, what do you mean by limit functions?
Like what are the activation functions? Like are they similar to the limit functions?
So I'm not basically clear about what limit functions, but like activation functions are basically used to add the non-linearity into the models.
Sir, like could you please give an example for like how are they used in the neural networks?
Oh, sure. So for example, yeah, you can take an example of sigmoid activation function, right? Okay. So how does this looks? So this looks like sigma x equals to 1 by 1 plus e to the power minus x. Okay. So, so for example, suppose this is your MLP and you have, and the activation function is the sigmoid activation function, right? So who was questioning? What was your name? Sorry, I
Sir, Hemant.
missed that. Hemant, yeah. So Hemant, like pause me whenever like it's not clear, right?
Okay, sir.
Okay, yeah. So suppose this is a MLP, right? So let's suppose this is 1 1, 1 2, this 2 1, and this is 2 2, right? Okay. So what will be the output? What will be the output of this layer?
1 1 and 2 1.
So yeah. So let's say Z will be, so x1 times, or sorry, I will do this way, w11 x1, right, plus w21 x2, okay, plus the bias term, right?
Yes, sir.
So this is clear? Yeah. So now we apply the activation function to this. Okay. So after applying the activation, say A Z, so it will be 1 upon 1 plus e to the power minus z, right? Where z is this term, the above term. Okay.
Okay, sir.
So the deeper your model, so your term becomes more complex. right?
Yes, sir.
So this is the main intuition behind applying the activation function. So
Sir,
this
is it
this
like we want a fixed value as an output, so we'll be using this?
no, see, so you know the graph of the sigmoid function. So I
Yes, sir.
think it's somewhat like this, right?
Tan
So
x.
see, yeah. So see, it's not linear,
Yes, sir. It is turning from minus infinity to plus infinity.
right? And it is adding the non-linearity to the model, right? You can see here.
Yes, sir.
Hmm. So does that answer your question, or like if you have any follow-up
Yes, sir.
questions?
I got it.
Okay.
Sir,
Okay.
and like, could you please explain what is biased plus B you wrote, right?
So the B is so you know linear regression, right?
Yes, sir.
So in linear regression, this is the same B. So Wx plus B. So this is the same bias which we
Okay, sir.
apply for
Okay.
every node. Yeah. The
Constant
bias
load.
is, yeah, the bias is a constant for every node. Okay. So for every node, there is just one bias.
Okay, sir. Thank you.
So for this, you have one bias, say, suppose B1. For this, you can have another bias B2. So we will see it with the help of example, which is coming soon. Yes, Krishnendu.
So, what's the range of sigmoid activation function, if you can say?
So range is from 0 to 1.
Okay, sir. Thank you.
Hmm. Okay, so let's move on. Okay, so let's see another example, which is the like two input AND gate. Okay, so for two input AND gates, say x1, x2, and y. Okay, so this is a truth table for AND gate, and let us plot it like before. So this is our x1 axis, this is our x2 axis. Um, right? So again, you can see that this is linearly separable, right? So above it, all are 1, and below it, all are zeros. Okay, so let's try to draw a MLP like before, right? So x1, x2, and this is your output. Okay, and let's say the bias for this node is minus 1.5, and let's say the widths are 1, right? Okay, so let's see for all the four cases again. So x1 is 0, x2 is 0. And again, like let's take the activation function as the step function. So if x critical equals to 0, otherwise, right. Yeah. So what happens for x1 0 and sorry, x1 is 0 and x2 is 0. So y becomes minus 1.5, right? And if you apply the step function, so it maps to 0 for a case 2. X1 is 0, X2 is 1, so y equals to minus 0.5. Okay, you can do the calculations. I'm not going into it, but yeah. So when you apply the activation function, it maps to 0, right? For case 3, it's the similar case as the case 2. So x1 is 0, sorry, x1 is 1 and x2 is 0. Y becomes again minus 0.5, and when you apply the activation function, goes to 0. Okay, and for the last case, case 4, what you have is x1 is 1, x2 is 1, and the y is how much? 0.5. Yeah. So it goes to 1. Yeah. And see, this is the MLP that solves the two input AND gate problem, right? Clear till here? Okay. Okay, now let's see one tricky case, right? So maybe we will see one non-linear case. Yes, Priyadarshini. Yeah, please. Priyadarshini, do you have any doubts? Yeah, please.
Yes,
Hmm.
sir. Sir, in the previous case, you took the bias as minus 0.5, and in this case, you took it as minus 1.5. So, are you choosing the bias randomly, or is there any specific rule of choosing it?
Yeah, so we are just looking at some examples. In this, we are assuming that we are given all the weights and biases, but we will like we will look up at a technique where we can like automatically derive these weights and biases.
Okay, okay, sir. Thank you.
Okay. Okay, now let's see at the two input XOR gate. Right. So x1, x2, and y 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0. So, two. Right. So you can see this case. So this is the plot of the two input XOR gate. So now how can you separate it linearly? Okay, so now what happens when you want to solve it? Okay, now let us increase the depth of the multilayer perceptron, right? Okay. 111. Right, let's say the bias on this is minus 1.5. This, let's say it's minus 0.5. And this is minus 2. So now let's say the bias on this is minus 0.5. Right. Okay. And let's call this node as H1 and let's call this node as H2. Right. Okay. So, like before, we will try to see all the four cases. So what will happen for x1 is 0 and x2 is 0. So first, and again, like we have the activation function like before, we have the step function 1 and 0 x equals to 0. Right. Yeah, so what will be the output at H1? So it's minus 1.5. Okay, for H2, it's minus 0.5. And when you apply the activation function, so it becomes 0, and this also becomes 0. So what is y? So y is 0 times minus 2 plus 0 times 1 minus 0.5, right? So when you apply the activation function, it again goes to 0. Okay, so this is how you solve the first case where x1 is 0 and x2 is 0, right? So for the case 2 and say case 3, because both are the mirror cases of each other, right? So let's say x1 is 0 and x2 is 1. So in this also, you can also take the x1 as 1 and x2 as 0. So this will give you the same results. Okay. So h1 is 1 minus 0.5 minus 0.5. And h2 is 0.5. Right. So when you apply the step function, it goes to 0 and this goes to 1. Right. So calculating this for y, so 0 plus 1 minus 0.5, that's equals to 0.5. Now this is 1, right? And for the last case, which is the case 4, so you have that x1 is 1 and x2 is 1. So at h1 you have 0.5, at h2 you have 1.5, right? This goes to 1, this goes to 1. And what we have for y is minus 2 plus 1 minus 0.5 is 1.5. When we apply this, right, it goes to 0. Okay. So in this way, you can see how this MLP solves the two input circuit problem. Right. Does anyone have any question? Yeah, Aditya, please go ahead.
So can you explain what is H here, like the
So,
calculation that you are doing?
so H1 is this hidden layer, right? And H2 I'm referring to as this hidden layer. So the output as this hidden layer is, I've used it as H1, and the output as this hidden layer, I'm using it as H2.
Okay, sir.
Okay. Yeah, does anyone have any other question, or we can continue further?
We know that A's or B can be written with like and or and not. So are we doing something similar over here when we are sort of like I can sort of see that one of the singular perceptrons look like looks like an and the other one looks like an or. Like I can see
Hmm.
some similarities. Is it coincidental or is it like it is supposed to be like that?
No, see, these are small MLPs, and you can interpret it. But like when the MLPs will be deep enough, okay. So for example, you can see like this is like just 2 layers deep. Sorry, yeah, like you have one hidden layer and one output layer, right? So how can you interpret it when the number of layers, hidden layers increase? So then at that time it will become very complicated. So these are just simple examples, but like in real life, uh, these MLPs like don't work. Okay, does that answer your
Okay, sir.
question?
Thank you.
Yeah, yeah. Okay, so I hope that you have understood with the help of these two basic examples, so how we can solve for linear and non-linear cases, right? Okay, but the problem is, okay, now let us understand like how things work. Okay, so I hope it is very clear from this example, but uh, like let's formally get into it. Yeah. So yeah, inputs are passed through the layers, through the input layer of the neural network. So as you all have seen in the example. Okay. So for each node, the weighted sum is computed like this way. Like the weights of the current node, yeah, followed by the output of the previous node, and a bias term is added to it, right? And then we apply an activation to it. So this becomes like activation function of this, the weighted sum. Activation function applied over the weighted sum. Yeah. So when you keep on uh, like when you keep on computing the weighted sum, and you proceed further, you go to the output layer, and the output is a prediction. So you can, let's say this is y hat. Okay. So yeah, the output can be a scalar, so, or a vector. So this is a vector output. So you have two outputs, right? So you will get some values out here. You will get some values like say 1.5 and 2.3 out here. But how do you interpret it? Okay, so for example, suppose you are doing a cat dog classification. So you have images of cats, you have images of dogs, right? So you have two output classes, one representing the cat and one representing the dog. Okay, so if you go on applying the weighted sum and the activation, so in the output you will get some numbers, right? So that can be a real number, that will be a real number. So in order to make it into a probability, okay, we apply a function which is termed as softmax. Okay, so which looks like this, right? So these ZIs are the outputs which we have in the output layer and divided by the total summation. Okay, so this is how logit is converted into a probability distribution, right? Okay. So for real life, how do we continue? So we initialize the weights randomly first, right? And we do one forward pass, which is like calculated when you do the weighted sum followed by the activation, and you keep on doing this until the uh, output layer, right? As we have also seen in the examples. But we want to find the optimal weights for which like our predictions are correct. Okay, so if it is a dog, then the probability of the lower node must be higher. And if it is a cat, then the probability of the upper node must be higher. Okay, so we want to get the best weights. So how can you do that? So for that, we have something that is called as backpropagation. Okay, the backpropagation algorithm. So what happens in the backpropagation algorithm is, so first we compute the output from the neural network, which is say y hat, and then you have a ground truth value. Okay, so for example, if you have a dog and a cat image, okay, and you have the ground truth as a one hot encoded vector. What is a one hot encoded vector? So in one hot encoded vector, the output for the dog will be 1 and everything else will be 0. Okay. Yeah. So for example, if you have a dog image, then the ground truth is 0, 1. And if you have a cat image, then the ground truth is 1, 0. So in that way, you can compute a loss between the ground truth and the predicted output. You can use there are multiple loss functions, so you can use any one of them. So mainly the MSE is used for the regression-based task, and the cross entropy is used for the classification-based task, right? So now we have to propagate the errors backward, right? So the loss is computed after the final output layer. So now we have to propagate the losses until the very beginning, right? So how do you do that? So you can do that by taking the partial derivatives, right? So I think you must be knowing the chain rule of differentiation. Okay. So if you know that, so what will be the output of this, the error at this layer? So it will be just the dl by dz of l. what is dz of L? Dz of L is just the weighted sum. Okay. And so, but you cannot differentiate it directly, right? Because it has also got the terms of this activation. So what we can do is we can break it into two pieces, which is the dl by over d of activation and d of activation over d of weighted output, right? So what happens for the hidden layers? Say, for example, suppose what happens for this node. Okay, so let me turn on my board again and we can see an example. Yeah. Okay, so for example, okay, so let's name it as H1 and let's name it as H2, right? So you do one feed forward pass and you have the output as Y hat. And then you also have the actual ground truth of the image or the data that you have taken. So that is a one part vector. So let us suppose this is it. So this position represents whether it is a cat or not. And this position represents whether it is a dog or not, right? So you have got the predictions, you have the ground truth labels. Okay, so yeah, so for this you just have one, right? So this won't work. You just have a y value, which is supposed to be any real number, right? And we are doing a regression task. Okay, let's think of it like this. So you have calculated the loss between the y and the y hat, the ground truth and the predictions. Okay, and you want to calculate the loss at the output layer, right? So del set O, but you cannot differentiate it directly, right? Because there is also the term for the activation. So then you have to break it up into activation at O, activation O, then D of set O, right? This is it. Okay. So everyone is clear, like what will be the gradient at the output node? Is it clear, or does anyone have any question? Hello. Does anyone have any question, or like it is clear? Okay, okay. Okay, now let us find the gradient at the H1. Okay, so what will be it? So del L by del set H1, right? Okay, so del L by, yeah. Does anyone wants to help me with this? Come on, it's just differentiation, so you can do it. So what will be this? dA of H1 times dA activation of H1 over d ZH1, right? Clear here? Clear until here? Okay. So now you can see that you can differentiate this term directly, right? This term you can differentiate directly, right? But what about this term? So can you differentiate it directly? Anyone? So I am repeating my point. So you can differentiate this term directly, right? The second term, this one. But can you differentiate this first term directly? Anyone? Yeah, but can you come up with a reason why we cannot do it, Arav? Or anyone? Anyone? Does anyone want to try why we cannot differentiate it directly? So I just have told you the reason. And the same reason applies for the hidden layer, hidden nodes too. So Himanshu is saying AH1 is dependent on the activation. Yeah, we have dealt with that, but Himanshu, understand this, like why we cannot differentiate the loss directly with respect to the activation at H1. So there must be activation at the node H1, right? So my question is, why we cannot differentiate this term directly? Simple, because like this is okay, the loss is first also dependent on the output of the gradient is also dependent on the output of this output node, right? This node. Exactly. So for that, you cannot calculate the gradient directly. You have to come via the output node, right? So this is the main reason. Okay, is it clear? Or if you have any doubts until here, please speak up. Or like it is a bit confusing thing. This topic is a bit confusing thing. So if you cannot understand any concept, please speak out. Okay, so moving forward.
Okay, so can you just repeat that why again we have to go to the output part?
Yeah, we cannot directly differentiate this term because like we have to come through the output first. The gradients of the output will impact the losses first, right? And then it will be impacted by the output of the node H1, right?
Okay, okay, understood.
Yeah. So how you can do this? So this will be TL by DZ of output times D of output D A of H1. and you have this term right here. So d of h1 over d sub of h1, right? So when the depth of the neural network starts increasing, okay, so you have to calculate this gradient also for the other nodes, right? Okay. So what is this part? So this part will be the del of L plus 1, right? I mean the next layer, right? The one to which it is connected. Okay. And what will the differentiation of the weighted sum of the output with respect to the activation of the input? So it is basically like this, right? So W, okay, let me be consistent with the terminologies. W0 A of H1 plus B. Yeah. So this term, is like this, right? So when you differentiate with respect to uh, activation function at H1, so what will it be? So it will just be the weights, right? Weights at L plus 1. Okay. And this is simply the derivative of the activation function at H1, right? So this is it, right? So this is your final result. So if something is not clear until here, please raise your hands. Why this all happened, if anyone has some doubts. Okay, I can see no hands raising up. So does it mean that you all have understood?
So what exactly is delta in this context?
So delta, so I have taken this term as the delta. Okay, so delta is just d of loss over the d of z at the out at the this node. For example, sorry, my terminology was not correct. So this should be at O, right? And so this is just this term. I am referring to this term. I am referring to this term as delta. Okay. So I'm just writing it in short. And this will be just O.
O is
Yeah.
the output node over here.
Yeah, exactly.
Okay.
So is it clear? So I think like you can compute the derivative of the sigmoid function or the activation function. Okay. And then you can slowly compute uh, the gradients and then propagate backwards. Okay. Until here. Right. So this is clear until here.
Uh, in delta O, you have written delta O is equal to this, and then after expanding, you have again written in terms of delta O.
Which one?
Or
This part.
Oh no,
This
I think this is what the last term that you have written is that delta H1.
no, this is sigma. Sigma. Are you
No,
talking
I'm
about
not
this
talking
term?
about that. The entire last boxed term that you have written, delta O,
Yeah.
W O, sigma dash H1,
Yeah, yeah.
that is delta H1, right?
That is, yeah, exactly. You have
Okay,
understood it.
thank you.
Yeah. So this is delta H1. Okay, so is it clear to everyone, or if you have any doubts, then you can please ask. Okay, so I don't think anyone has any doubt.
The result from activation function that comes from H1 that depends on the input. Then why we are considering the output node here?
So because like in the feed forward, okay, so we have moved in this direction, right?
Yes, sir.
And now we are back propagating. So we are moving in the reverse direction, right? So first the error is computed for this node, okay, and then we like move backwards slowly. So we propagate the error to this node, and then this node, and then all the previous nodes, and so on we move, right?
Yes, sir.
So for that reason, so the output of at the so the output at the O node will impact the error at the O node will impact the error of the H1 node, right? Sorry.
Yes, sir.
Yeah.
In the back.
I exactly. So
Okay.
we just propagate the error backwards, right? So from here we have first got the y hat. Okay. So we have computed the loss, and then we are propagating all the error backwards towards the uh, input layer until the input layer. Sorry.
Okay. So this is we do to update the weights, or matlab, what is the purpose for this?
So as I said that we want the best weights so that our predictions are optimal. So for example, say a dog should be given a dog as output and not a cat as output, right? So
Yes.
for example, if you have this features, okay, and suppose this is your MLP and these are the outputs, right? These are the outputs. So suppose this represents the dog and this represents the cat. Okay, so when I give input a dog picture, so this output should be 1 and this output should be 0. And if I give the input of a cat, then this output must be 1 and this output must be 0. So we want such weights, okay, which will approximate the function so that the dog is shown as a dog and the cat is shown as a cat. Okay. So what are MLPs basically? So these are just function approximators, right?
Yes, sir. Okay.
So is it clear, Himanshu?
Yes, sir. Yes, sir.
Okay. Okay. So does anyone else have any questions, or we can proceed further? Okay. So now we have calculated the gradient for each node, right? But what we want is what we want to calculate the gradient for the weights, right? Because ultimately we want to update the weights, right? So once we have calculated the gradients with respect to the output, okay, so ultimately we want it for weights, right? So we can write this like this way: dz of O over d of W. Right. So this is where we want to ultimately reach. So we want to find the gradient for each weights. So this is our ultimate step. Okay. Okay. Let's set this. Yeah. Okay. So if you can follow the text over here. So I think you are familiar with this term now. Del L equals to WL plus 1 delta L plus 1 into what I said. Okay. So you want to compute the gradient of loss with respect to the weights, and you can do it this way, as I told you. So I hope that you can calculate this by using all the terms above. Right. Now, once we have the gradients of all the weights, gradients of loss, so what we can apply is a gradient descent function, right? So what we can do is we can update the weight in this manner. So like we have started with all the random weights, and then as the training progresses, so the weights can be updated, like the previous weights can be updated by subtracting the gradient of loss, okay, with respect to that weight. And this eta is just the learning rate, right? So you can update your weights in this manner, and this continues. Okay. So how the training proceeds is, so first we do the forward propagation, then we calculate the loss, then we do the backward propagation, and we keep on doing this for multiple epochs. So a new term is epoch. So what is one epoch? So one epoch is like one complete pass through the entire training data set. For example, if you have 1,000 data points in your data set, okay, and if your model sees all the 1,000 data point once, then it's termed as one epoch, right? So we keep on doing this over and over for multiple epochs. So we do the forward pass, we calculate the loss, we do the back propagation, and we do the weight updation, right? In this manner, we finally achieve the optimal weights by which we can say that a dog image corresponds to a dog and the cat image corresponds to a cat, right? I hope it's clear until here. If you have any questions, so you can raise your hand, else we can continue. Okay. Okay. So we have one weight updation demo. So this is a link from Geeks for Geeks. So I would like to quickly show you this. Okay, you can see the example, uh, like example which is done in this Geeks for Geeks website. Okay, so in they have taken a weight, taken the weights, taken a MLP with weights, and they are passing a input to it, and they are calculating the forward propagation and the backward propagation, right? So this is a worked out example. I am sharing you the link in the chat. Maybe you can have a look at it once. Okay, so this is a worked out example, and in this you can better understand how the weights are updated. So, okay, take 2-3 minutes for quickly viewing this, right? And we will then continue with our class. Okay, also if anyone has any questions in between, can ask. Yes, sure.
How exactly learning rate is determined?
So this also is based on a trial and error basis. So basically, like it's different for like different architectures. Okay. So for example, you can say that for VITs, it can be 0.0001. Okay. Like 10 to the power minus 4. For ResNet, it is 0.001. But you can like make changes to the learning rate and you can see how the training proceeds. Right. So basically is okay. I'm not going deep into the gradient descent technique, but I will just share an overview with it. So for example, like this is the place, suppose, where you have the minima, right? And your weights are currently here, right? So uh, so learning rate determines how fast or how slow you move towards this minima point, right? Okay, so the larger your learning rate is, the faster you move towards the minima, and the the lower your learning rate is, the slower you move. But like you can also face some problem if you have larger learning rate. So for example, you can come here and then maybe your model can skip here without going here, right? So this is the problem that you can face. So for that, you need to make adjustment to the learning rate and then proceed with the training. Does
So
that answer your
basically, it
question?
doesn't
Hmm.
always guarantee convergence, right?
Yeah, so you have to try out with some values, and yeah, so the best, so you just keep the best values, like the learning rate for which you have the lowest loss, right? Shrek, does that answer your question?
Can you repeat the last point? Didn't get it.
Okay, so I'm just saying like you can make adjustments to the learning rate and then you can continue with the training. So for the learning rate, which you have maybe the lowest loss, that you can keep as your best learning rate.
Yes, but
So, okay. Okay, so we move on with next. So have everyone seen that example, gone through that example? Okay. So the next thing we will see is like the training of a neural network. Okay. So for training a neural network, the main thing which you need is data, right? And let us look at one example dataset, which is the MNIST dataset. So it is a image classification dataset for handwritten digit recognition, right? So you can see this image. So these are all the handwritten images that are there in this dataset. Okay. So the number of classes are 10. So you know 0 to 9. The images are of size 28 cross 28. It means you have 28 rows and 28 columns, right? And the color is grayscale. So do you know the difference? So have you learned about images in your previous classes, like the grayscale images and the RGB image? No. Strange. Okay. So okay, so this is how our image is represented. So image is just okay. Okay. So I'm just going briefly through what images and how it looks. Okay, I won't go into more details, but like you will have a basic understanding about images. So what is image? So image is just a 2D matrix, okay, where each each cell, or you can say each row and column location, this represents a pixel value. Okay. So these for a 8-bit images, for a 8-bit image, the minimum value is 0 and the highest value is 255. Like 0 indicates complete black and 255 indicates complete white, right? So for a grayscale image, you just have one 2D matrix. And if you stack three of the grayscale images together, stack means keep above each other, right? So one for your red channel, one for your green channel, and one for your blue channel, then it forms a RGB image, RGB colored image. So is this basic part clear? Uh, have have you understood it? Okay. Okay. So we will consider this MNIST dataset, so which has 10 number of classes. The image size is 28 cross 28. It means the size of the 2D matrix is it has 28 rows and 28 columns, right? So what are the total number of pixel values? So it's 28 cross 28 times 28, which is 784, right? Okay. So the color is grayscale. It means you just have one channel. Okay. The number of training images are 60,000 and the number of test images are 10,000. Okay. And you can guess the label. So the label is the number that the image is representing. Okay, as simple as that. Okay, there is one question. Sir, can you explain the mathematical concept? Node logic. Uh, Deepan, can you please specify which mathematical concepts are you talking about? Like regarding what? Like the error correction. So, like, do you mean the backpropagation algorithm? Okay, so I've already explained it and I've also given you a worked out example. So if you have any doubts in what I taught you, so you can just ask me, and I can answer your question. Okay, so okay, Deepan, we can do like this that at the last of this class, I will give you my mail ID. So if you have any doubts while studying or understanding any concept, so you can just send me a mail so I can get back to you. Does that work? Okay, okay, fine. Okay, so yeah, so I think I've explained you about this data set, the MNIST data set. Okay, now training the model. So our input is the images from the MNIST data along with the ground truths, okay, which are the digits that it represents. And our output must be the model trained on the MNIST data set, right? So what we do is first we initialize the model. What does initialize the model means? Like we set the weights randomly, as I told you before. Okay, so we decide upon a loss function. So the loss function could be something as the cross entropy loss or any other loss which you know. Okay, define optimizer. Okay, let's suppose this is gradient descent for now, right? So we will iterate it over several epochs. So for epoch in range, number of epochs. So you can iterate it for how many epochs you want. And now for batch images, batch labels in training data. So you just pick out a mini batch. Okay, so okay, let me give you the concepts of batch. So why do you need a batch? So we, as you know, that we have limited size of RAM, right? Limited size of RAM, computer RAM. But you know that the data sets are usually very big. Okay, so suppose you have data. So suppose all the laptops now have 16 GB of RAM commonly uh, within them. Okay, but the data sets are too large. So suppose you have 500 GB of data. Okay, so what happens is you cannot load the complete uh, data into the RAM and then do the processing. Okay, so for that, what we do is we just pick up some images, we train the model, and then we discard it, and then we just calculate the loss, and we then take another set of images, load it, calculate the loss based on that. Like we train the model based on those images, and then we just take another set of images, right? So this is how we uh, we train with the limited uh, like the limited configurations that we have, right? So for each batch of images, we first the predict the output from the model. Okay, so which is just the y hat that I had explained you before. We just calculate the loss using this loss function, and then we just uh, do the back propagation, and in the optimizer step, we just update the weights, right? So this continues for several epochs, and then at each epoch, you can also evaluate on the validation set. So why it is done? So you want to get a flavor of how your model performs, right? So for that, you need a separate set with which you are not training. So that set is called the validation set. And you can evaluate your model on the validation set, and you can get a performance uh, if you can get a performance estimator, like how your model is performing. Is it good or is it very bad, right? Okay, one question. How we know that we have reached the minimum? So you cannot know how, like you cannot know if you have reached minima or not, because the like for a function you don't know what its minima is. But yes, we can keep on training for multiple epochs, and then wherever our loss is the lowest, so we just keep that model. You never know actually like what your minima is, actual minima is. Yeah, you just keep on trying for various hyperparameters. You just change the maybe you can change the learning rate, maybe you can change the weight decay, and there are various parameters. Maybe you can even change the loss function. Okay, sir, can you please explain? Yeah, I'll come to it. I'll come to that. Okay. So have you understood this training part? Okay. So let's go to the testing part, right? Sir, what is an optimizer function? Okay. So the optimizer function, as you have seen, is the gradient descent that we had discussed earlier. Okay. Which is used for your weight updation, and that you can use to like get the optimal weights for your model, right? Okay. Okay. So during testing the model, like you have to load the trained weights, you have to load the trained model, and you have to load the weights. Okay. And you have to freeze the weights so that no more updation works, right? Then for each image, we just predict it. We just like do a feed forward. Uh, we just predict the output from the model, right? And we just compute the softmax, which gives us the probability distribution. And maybe you can take the argmax to calculate which which index is the highest, right? So is it a dog or is it a cat? So you can determine from that stage, right? And you can display the predicted class. Okay. So sometimes you need early stopping also. So what is early stopping? So suppose when you are training, right, your loss is decreasing, decreasing, decreasing. And after a certain period of time, say after say 10 epochs, your loss has stopped decreasing and now your loss is increasing. Okay. So you can wait for a number of steps, number of epochs, and that is called the patience, right? And then if say suppose if your patience is 5, and after the 10th epoch, you see that all your weights are increasing again, or your losses are increasing again. Okay, so you wait for 5 epochs. So if after till 5 epochs, your model does not have a better loss, so you just stop the training, right? So that is what is known as early stopping. Okay. Since the minima is not known, it's stages. Yeah, Shreyak, in that case, maybe you can save the model for each epoch, and then you know after running for say 100 epochs, which is the best, so you can pick up that model that fits. Okay. Okay, so what are some of the shortcomings? So some of the shortcomings is that, okay, so if you want to input this image into a multi-layer perceptron, how you can do it? Yeah, does anyone wants to take a try? How you can give this image as input to a multi-layer perceptron? So it's simple, right? You just stack all the rows, okay, one after other, one after another, one after another, and this gives you a column vector, right? Yes, exactly. Yeah, sure. So you can just stack it row by row, or you can stack it column by column, and then you can pass it to the multi-layer perceptron. But what that does is, like, the spatial relations are not preserved. Okay, so you can get that. So when you stack it, you are like just completely destroying the spatial relation. And for large image, we have to train too many parameters, right? So for C 28 cross 28 image, you have to train 784. You have the input dimension of 784. Okay. And just understand that today's image is minimum of 1000 cross 1000. Minimum image sizes of 1000 cross 1000. So you can understand like how big the image will be and how many parameters you have to train, right? So the question is, can we do better? Okay, so there comes convolution. So what is convolution? So this is a mathematical operation which can be used to extract spatial features from input data. For example, in convolution, you have a filter, which is also known as the kernel. You place it on an index location, you just calculate the dot product, and you just sum it up, right? So for example, suppose this is the filter, -101, -101, -01. You just place it on the index location, which is 4 in this case. You just compute the dot products, right? So what will be the dot product? So it's 2 times -1, 3 times 0, 4 times 1, 5 times -1, and so on, right? And then you just sum them, and your result is 2. Okay. And you just calculate it for all the spatial locations, right? So we will introduce two more concepts here. First is stride, and second is padding, right? So padding is if you want to increase the size of the image so that your filter can also work on the boundary pixels, right? So that is what is called as padding. Okay, so we can pad it with like zero vector on 4 sides. There are like various type of paddings. And stride is how many steps we move to the left or how many steps we move below, right? So uh, if you have a stride of 1, that means like after applying the filter at this 5 position, then it will move to 1. It will move 1 step to the right. Okay. And then it will again move 1 step to the right. And then it will go 1 step at the bottom. Okay. And so on. It will compute for all the spatial locations. But if you have a stride of 2, so what will happen is first the convolution is calculated for this location, and then you will move 2 steps. So you will go at 3, right? So this is how the things work. Okay. So we have the padding 0 and we have the stride as 1. So after you apply the kernel to all the spatial locations, the final output is somewhat like this, right? Okay, so what is the kernel for the boundary elements? Okay, so as I already said, for the boundary, you cannot apply the convolution directly, because suppose you place the kernel in this location, so you don't have anything to operate on these locations, right? Because here is nothing. So in that case, you can use padding. Okay, you can pad it by 0 vector, or you can also do mirror padding, in which you just mirror the bound these elements into the padding vector. Okay, so in this way you can like also operate for the boundary values. Right, Udvash, it is clear? Is it clear?
Yes, sir.
Okay. Okay. So now let us suppose we have a colored image, right? Of size say 64 cross 64. So we write it in this way. So 64 cross 64 cross 3. So 3 is the number of channels. So in this case, you can consider the red, green, and blue channels, right? And you want to apply the convolution, right? So what will be the filter size? So the filter size must be 5 cross 5 cross 3. Or you can take any other size also, say 7 cross 7 or 11 cross 11. Okay, it's as your wish. So for example, we have taken 5 here, and the size of the filter is 5 cross 5 cross 3, right? So you just take a dot product, okay, with every spatial location in the image, right? And then for one filter, you have one feature map, right? Okay, how are the filter values determined? Okay, so the filter values are automatically learned during the training process. What impact does the different filters have here? Okay, so like the different filters extract different type of features from the image, right? That is the main intuition. And how can we find the optimum filter? Okay, so the filters are learned during the training process. Okay, so after you get the best model, you can expect that you have the best weight for the filters, right? Hmm. Is it like during numerical training we update the weights? Here also we update filter values. Yeah. So these are all the you can think of it like weights. Okay, these keep on updating. Okay, so moving forward, say for example, suppose you have a RGB image of size 64 cross 64 cross 3, and you want to have like 6 feature maps from that image. Okay, so what you do is 6 activation maps, right? So what you do is you just convolve the filter. Okay, and how many filters do you need? You need 6 filters, right? One for each feature map. So for for 6 filters, you have 6 feature activation maps, right? Okay, can anyone tell like why for 64 cross 64 cross 3 the output is 60 cross 60 cross 6? So why it is not 64 cross 64? Can anyone explain? Yeah, exactly. Krishnendu, you are right. Because we have not used any padding for our image, and we have used the 5 cross 5 cross 3 filter. Right. Okay, so let's see like have we improved or not. So if you wanted to use a fully connected MLP layer, okay, so what were the number of parameters that you had to train? So it's 64 cross 64 cross 3, okay, and the output should be of 60 cross 60 cross 6. So all gets multiplied, and you have nearly 265.42 million parameters that you have to train, right? If you want to use a MLP for training, just this step. Okay, then we also have like the later part of the model. But if we apply the convolution part, so you can see that the size of one filter is 5 cross 5 cross 3, and we apply 6 filters. So we have to train only 450 parameters. Can you imagine the difference that we are achieving? And if we like multiply it over all the spatial locations, so these are the number of multiplications that we have, total multiplications, in compared to the fully connected MLP, in which we have 265.42 multiplications. So can you see this massive difference? Okay, so like before, what we do is we first use the convolution, and then we use the activation function to add some non-linearity, right? So which is helpful for accomplishing uh, some complicated task. Okay, so how it proceeds is, so we first take an image, we apply the convolution, and then we use the activation function. In this case, it is ReLU. We get the feature activation maps. Then we again apply convolution to it, and then we again apply activation function to it, and this keeps on continuing. Okay. So we will see an example after some time. Right. Okay. So another terminology in this CNN is the pooling layer. So what the pooling layer does is, so it basically downsamples the image. Okay. So there are various type of pooling. I mean, say you can think of it like max pooling, mean pooling, average pooling. Okay. So they are just used for downsampling the image. So you can represent the 60 cross 60 image, say suppose to 30 cross 30 image. So how we can do it? So suppose, let us see an example. Suppose we have a feature map, say 1, 3, 6, 9, 2, 4, 5, 2, 8, 7, 5, 14, 11, 2, 8, 0. Okay, so let us consider a 2 cross 2 max pooling with stride 2. Okay, so what I explained you with stride 2 is we will shift 2 places to the right and 2 places to the bottom every time, right? So when you have the 2 cross 2 max pooling, so you take this 2 cross 2 pixels first, you take the maximum. So what is the maximum? 4. Okay, you just write it down. Then your stride is 2. So you move to the right, and now your 2 cross 2 window is here in the green. Okay, so it's 6952. So what is the maximum value over here? So it's 9, right? So now you go here. Okay, because it's a stride 2, so you move 2 steps down and you come here. So it's 8, 7, 11, 2. You take the maximum, and for the last you have the maximum as 14. Okay, so in this way you have represented a 4 cross 4 image with just 2 cross 2, right? Okay, so do you have any doubts until here? So you can ask. Is it clear until here?
Sir, how does the stride move? Like after 6952, or does it
Mhm.
come to the new boundary of the 8711 or 51480 first?
No, so it moves like row by row. So 1324, then 6952. Okay, then next we move 2 places down, right, due to stride 2. And then
At the
again
beginning of
we,
the means at the beginning of the column, zeroth column again.
yeah.
Okay, sir.
Okay, so have you all understood this part? Okay, okay. So let's move further. So this is a basic encoder and decoder architecture. So autoencoder architecture, which is also called as the encoder decoder architecture. Okay, so we will learn more details about this in tomorrow's class. So for today, just note that a encoder is a function that maps the input to a latent representation. Okay, for example, suppose you have this uh, 784 dimensional input. Okay, so you can map it to a 100 dimensional latent space, right? And from that latent space, your if you try to recreate the image back, so that you can call as the decoder, right? So input, we have the encoder, we have the decoder. Okay, so now let's see some examples of uh, the CNN models. Okay, so this is a model which is known as the AlexNet. So it was introduced by uh, Alex Krzyzewski. So it is uh, they have named it AlexNet. Sorry for the mispronunciation. Uh, so this is the input data. So you have first convolution. So this converts the image of 227 cross 227 cross 3 to 55 cross 55 cross 96. Okay. So the three channels are converted to 96 channels. And then you again downsample the image to 27 cross 27, and the number of channels are increased to 256. Okay. So this keeps on continuing. And then after the convolution 5, you just flatten the image, right? Flatten the features. So yeah, you just flatten the features into 4096 dimension, and then you forward propagate it, and then your fully connected it. This is the final output layer, which has 1000 nodes, right? So this is a very famous model, and you must have heard this name, which is the ResNet 50. So this has 50 layers, and it also has skip connections. Okay, so the gradients can move smoothly, right? and this is the final output layer. This is another famous model, which is the VGG16. So this was introduced by Zisserman lab. Okay, so there are multiple applications of. Okay, so how the channels are increased and how these features are flattened. Okay, so I have already explained you how the channels are increased. So suppose you have a 64 cross 64 cross 3 image. Okay, and you want 6 feature activation maps. So what you can do is you can apply 6 different filters, right? So, okay, let me talk in respect to that model. So you have 227 cross 227 cross 3. Okay, so for converting to this, you need 96 different filters. Okay, so each filter may be of size, say, 3 cross, like 5 cross 5 cross 3 or 3 cross 3 cross 3, right? And then how you can flatten this? So this is the way, like we have seen how we can flatten the image and pass it to the MLP. So this you can consider of it as a matrix. So you can flatten it by the rows and then stack it and then pass it to the fully connected layer. Right. Okay. So these are some of the examples. So of CNN. So it can be used for image classification. So we have seen some models for image classification, right? So where you pass an input image and then they are applied through this encoder, and then we have the fully connected layers and then a final output layer, where the final output layer is a vector of length n, where we apply the softmax and that shows the probability distribution for each class, right? So we have object detection. So what happens in object detection is, so you classify the object and you also predict the bounding box, right? So to localize the, like, localize the object, right? So you can see that this bounding box better represents the object, which is car, right? So you can use this for image segmentation. So see, this has segmented the person and the cycle separately, right? So what is the output in this case? So the output in this case is just a probability map for all the n classes, right? Where each pixel gives you a probability of that pixel belonging to that class, right? Okay, so here are some other examples which are like image compression, image denoising, and you must be knowing various other things. So the face detection is also application of CNNs, right? Okay, and okay, as we come towards the end, I will like to take a short topic, which is the transfer learning. So you want to use the ability, you want to use your training, okay, for a new problem. So for example, in real life, if you know mathematics, so you can learn machine learning. If you know how to play badminton, you can play tennis. And if you know how to ride bicycle, maybe you can know how to ride a motorbike, right? You can use that knowledge to ride a motorbike. Okay. So the idea is, so instead of learning 2 different tasks, okay, so you can use the knowledge from task 1 to the task 2. So then you're like uh, training, you can like optimize faster. Like the the model has better weights as compared to learning from scratch. Okay. So the basic idea is take a deep neural network, train on some data set for a source task, and then adapt the network for your data set and for your target tasks, right? So for example, you have a data on cats and dogs data set, okay, and uh, you can apply it for classification of say some other, say for example, lion and deer data set. So you can use the weights of that model. Okay, so with this, I end today's class. If you have any doubts, so you can unmute yourself and you can ask it.
Sir, while stacking the image means pixel concept, we are increasing the dimension in a way means if it is a 28 cross 28, stacking means we are increasing three more dimensions to it. मतलब adding three more layers to it. So we can say that the resultant will be 3 cross 28 cross 28.
Yes. So for a grayscale image, you just have one channel. So one two-dimensional matrix, and for a color image, you have three of the two-dimensional matrix. One for the red channel, one for the blue channel, and other for the green channel.
And number of pixels will be 28 cross 28 or 3 cross 28 cross 28.
So you can say it like 28 cross 28 cross 3. Okay. But when we will see in programming, so they have different ways to represent it. So they represent by like writing the number of channels in the first, and then they write the spatial dimensions. So they write it as 3 cross 28 cross 28. But if you can talk about it like 28 cross 28 cross 3.
Okay. Thank you.
Hmm. Okay, does anyone else have any doubt? You can talk and talk about it. Or okay, so my mail ID